AP Calculus BC, Unit 5, Day 13, Office Hours. So we're doing a little more related rates. I should check your answers already, but I will show them very briefly. Pause the video if you need to check them. That's the first one. This is the next problem, hot air balloon. This is the third problem, oil slick. And this is the last one, the cone. Okay. So let's do these. All right, a coffee pot has the shape of a cylinder with a radius of 5. Okay, as shown in the figure below, let H be the depth of the coffee in the pot measured in inches, where H is a function of time measured in seconds. The volume of the coffee in the pot is changed at a rate of -5 cubic inches per minute. Now, this is weird that they give us a negative. Usually they'd say it's decreasing or some other word to indicate that it would be negative, but they are giving us the dVdt. dVdt is -5 pi square root h cubic inches per second. Give you the volume, which you guys should be able to figure out. And they want you to show that dH dt equals -square root of h over 5. Essentially, they're telling you the answer. They could have just said find dH dt in terms of h, but you're doing that. They're pretty much telling you the answer. That's what you should get. So we gotta take the volume of the cylinder, pi r squared h. Are there any constants? R equals 5 all the time, no matter what. We have dVdt equals -5 pi square root of h. So we're going to rewrite this 25 pi h. I'm going to take the derivative implicitly. dVdt equals 25 pi dH dt. And we have an okay. So we're going to plug this in for dVdt and then solve for dH dt. So we have -5 pi square root of h equals 25 pi dH dt. Divide both sides by 25 pi. Pi's cancel. That reduces. And we get dH dt equals -square root of h over 5, which is what they said it would be. Here you go. B says, given that h equals 17 at time 0, h0 equals 17, this initial condition, solve the differential equation dH dt equals the -square root of h over 5. This doesn't rely on part A. You could have skipped part B. This is less related rates, more differential equation. So to solve a differential equation, you have to separate the variables, get the h's with the dh's. Usually leave everything else on the right side for the dt's. Separate the variables. Then we're going to integrate both sides. Now, this I'm going to think of as h to the -1/2. So that's going to be h to the +1/2 divided by the new exponent multiplied by the reciprocal, -1/5 t plus c. Now let's find the c now by using the initial condition. So if I plug 17 in for h and 0 in for t, I get my c value, 2 square root 17. Plug back in, rewrite it, 2 square root of h equals -1/5 t plus 2 square root 17. We're going to divide both sides by 2. And then we are going to square both sides. And h of t equals -1/10 t plus the square root of 17, all squared. Now, when you solve a differential equation, you're expected to supply the domain. So what's the domain? Well, are there any issues here that would cause this to be undefined for any reason? No. Go back to the original derivative. Are there any values of h or t that would make the original derivative undefined? Yeah. H has to be greater than or equal to 0, which also makes sense in the real world. And you might also have to apply real world restrictions to the domain. Time can't be, the height can't be negative. Also, time can't be negative. But h has to be greater than or equal to 0. You can't have a negative height. So we should probably figure out the time, because domain should be time, the time when h is 0. So the way you do that is you'd set h equal to 0. You'd set h -1/10 t plus square root of 17 squared equal to 0. Then you'd solve. You take square root of both sides, plus or minus -1/10 t equals negative square root of 17. T equals 10 square root of 17. So this is the time when the coffee pot's height is 0. So I would say the domain for this problem, would be 0 to 10 square root 17. But the domain for the solution of differential equation should always be an single open interval. I would say that maybe we could include time equals 0 because that wasn't an issue of where to break it up. But I don't know. And the units of these are seconds. Units of this is inches. Okay, part C, which I think actually is what we already did, was at what time is the coffee pot empty? Well, when is the coffee pot empty? When the height is 0. So it would be the work that we just did. I'll just redo it. They used to not always ask for the domain on solutions of differential equations. Now they do. So you set your height to 0, square root of both sides, plus or minus. Units are always important. That is when the coffee pot is empty. All right, next one. Hot air balloon, table of values. Now, we haven't done any tables of values for a long time, but back in calculator B, it usually means you're going to use estimation techniques. Riemann sums, estimating derivatives by slope of a secant line, often using estimation techniques. So the volume of a spherical hot air balloon expands, so it's getting bigger, as the air inside of the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function. We might need that for justification. The second derivative exists everywhere, which means the first derivative exists everywhere and is smooth, and means the original function is continuous and differentiable. Time 0 to 12, the graph of R is concave down. Might need that for something. The table above gives selected values of the rate of change R prime. Derivative R of the radius of the balloon over the time interval 0 to 12. The radius of the balloon is 30 feet at time 5. So that's probably an initial condition that we'll need for something. Volume of the sphere, radius R is 4/3 pi r cubed. A, no surprise, estimate the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give a reason. So often when we estimate, we're asked to decide if it's more than it should be or less than it should be, and there's different ways to decide that. So we need a tangent line approximation. at 5. So we got to write a tangent. We got to come up with the equation of a tangent line at 5. So we need the tangent line at t equals 5. Now to get the tangent line, you need two things. You need the point, and this is the tangent line for the radius. So we need the radius at 5, which they told us was 30, right? Was 30. And we need the derivative at 5, which if you look it up in the table is 2.0. You just look it up in the table. So you can write your tangent line approximation. Usually we use y, but we're going to use r this time and t. So point slope form be r minus 30 equals 2.0 t minus 5. And then we should probably go ahead and solve for r. And this is going to be approximation. 2.0 t minus 10 plus 30 is going to be plus 20. So that's our tangent line. So we want to use that to estimate the radius at 5.4. This is an estimation, so that symbol is most appropriate here. And so we get 10.8 plus 20, and we get 30.8. The units are feet. I'm always going to put the units. R 5.4. Label your answers. Now, is it an overestimate or an underestimate? So tangent line approximations are all about concavity. And I wouldn't memorize it. Well, I'd remember that maybe it's related to concavity and just do a rough sketch. It told you that the whole time that the graph is concave down. So any tangent line on a concave down curve is going to be an overestimate above the actual values. So this is an overestimate, and you have to justify, give a reason for your answer. Overestimate, since R is concave down on 0 to 12. Okay. B says find the rate of change of the volume of the balloon with respect to time when t equals 5, indicating a rate of change of the volume. So we're looking for dv dt at time 5. So we have a volume formula that they actually give us for a sphere, 4/3 pi r cubed. So we need to take the derivative of that implicitly with respect to time, which isn't too bad. And specifically at time 5, we know the radius is, we just used it, is 30. We know dRdt is from the table 2.0. So these are just using the same values we just used. So that's going to be 900, 3600, 7200 pi. The units are got to be cubic feet per minute. So that's sort of the related rates part of this problem. Usually related rates is just like one part now of a larger problem like this one. Use the right Riemann sum. Those are rectangles with 5 subintervals indicated by the data in the table. Approximate the integral of the derivative using correct units. Explain the meaning of this in terms of the radius of the balloon. This is a very classic question with the table problem. So I like to draw a little graph just to help me do this. Now it says there's 5 subintervals, 1, 2, 3, 4, 5. So we're just using all values in the table. And so I like to draw a little table, draw a picture of a chart here. So we got 5.7, 4.0, 2.0, 1.2, 0.6, 0.5. I'm not trying to make it accurate or anything, just relatively looks correct. This is just to help me. This is not going to give me any points. Any work on shown here I shouldn't depend on for points. Right Riemann Sum means we're using the right side for each rectangle to find the area. Right, so we're not going to even use this one this time. So we need to set this up. This is an estimate. So 0 to 12, let's label our work. R prime t dt is approximately, now the bases of all these are changing. So this was 2, 5, 7, 11, 2. So the base of this one is 2. Base of this one is 3. Base of this one is 2. Base of this one is 4. Base of this one is 1. So base times height, 2 times 4.0 plus 3 times 2.0. And this is work you need to show. You need to show this to get full credit for setting it up. 2 times 1.2, 4 times 0.6, and 1 times 0.5. This is going to be 8 plus 6 plus 2.4 plus 2.4 plus 0.5. So this is going to be 14, 4.8, 5.3. This is going to be 19.3. So I'm going to relabel it, make it super clear what this represents, use the appropriate symbols. Approximation. The units are, well, just using unit analysis, the units are R prime or feet per minute times dt is minutes. So you should be getting feet just based off that. But also it should make sense that if you integrate R prime, the derivative of R, and this is what's going to come next, you're going to get the change in R. So when you integrate a derivative, it's a fundamental theorem of calculus. Part 1, if you integrate a derivative, you get the original function. If you integrate from here to here, you're going to get the difference in f. So this is FTC part 1. If you integrate a derivative, you can get the change, the overall change in the thing. So it says using correct unit. So we don't need to use the value we got. It doesn't say to describe your estimate. They just say, what is this? This is not an estimate. This is the change in the radius of the balloon. You use context here. Don't just say R, radius of the balloon in feet. It says using correct units. That's not enough. From time t equals 0 to t equals 12 minutes. You have to have all this stuff. You got to describe the time. You got to put all the units. You got to use the context. So that's what we're looking for on C. D, is your approximation part C greater than or less than the actual value? So now we're trying to decide if this is greater than or less than. Now, just from our picture, you can get a pretty rough idea that it is an underestimate, right? I mean, this is not in any way a perfect graph or anything close to it, but you can tell graph is going down. Now, you got to know for sure that it's going down the whole time. And do we know it's going down the whole time? Do we know that R prime, this is the graph of R prime, do we know that R prime is decreasing? Because a right Riemann sum with a decreasing graph is going to be an underestimate. A left would be an overestimate. Increasing is different. So you just, I think you just drew a picture. This is clearly an underestimate, but we have to describe it. So we have to decide, is R prime actually decreasing? You can't just rely on those numbers and say, oh, well, they're all getting smaller. You got to know for sure that even in between it, it's happening. They told you that R was concave down. So since R is concave down, which is the same thing as R double prime of t is negative on 0 to 12, then r prime of t is decreasing. If the derivative of this is negative everywhere, then that is decreasing. And therefore, a right Riemann sum, you have to be specific about which side it is. Right Riemann sum will be an underestimate. So there you go. I had a lot of fun old stuff that we need to be good at anyways. Okay, oil slick from a pipeline on the surface of a lake and forms an oil slick whose volume is increasing to concentrate 2,000 cubic centimeters per minute. So they've given us dVdt. dVdt is positive 2,000 cubic centimeters per minute. The oil slick takes the form of a right circular cone cylinder with both its radius and height change over time. So it looks like this. You might think it's kind of a thin, but it says it's getting bigger this way and this way. The volume of a right circular cylinder is pi r squared h. Okay, we should be able to come up with that. Good. At the instance when the radius of the oil slick is 100 centimeters, r equals 100 centimeters, and the height is 0.5 centimeters, and the radius is increasing, dr dt is increasing at 2.5 centimeters per minute. At this instance, what is the rate of change of the height of the oil slick with respect to time in centimeters? So we're trying to find dh dt. So I've summarized all the information. So we probably got to bring in volume, pi r squared h, and I don't think we can get it in terms of a single variable, so let me just take the derivative the way it is. You got to do product rule, pi r squared dh dt plus h times derivative of that's going to be 2 pi r dr dt. We're looking for this. We have the radius, we have the height, we have dr dt, we have dv dt. So we have everything. So positive 2,000 equals pi r is 100 squared dh dt plus h is 0.5 times 2 pi r is 100 dr dt. Pi and 2 cancel each other out. So let's see, we get 2,000 equals 10,000 pi dh dt plus 100 pi now dr dt we should plug in also. dr dt is 2.5 positive. So that's going to be 250 pi. So we're going to subtract this to the other side. And then we're going to divide both sides by that. So 2,000 minus 250 pi divided by 10,000 pi. We could reduce it. We could take a 10 out of everything. Probably take a 25 out of everything. 25 of this would be 8 25s. That would be 1. 25 is in 1,000. Well, 25 is in 100 is 4, so that would be 40. So dh dt reduced is 8 minus pi over 40. The units are, h should be one-dimensional length, centimeters, time is minutes. And it came out positive, which I think it should because things are increasing. Okay, B says a recovery device arrives at the scene and begins removing oil. The rate of which the oil is removed. This is starting to sound like a rate model problem where you have incoming rate, outgoing rate. It's really just a differential equation of two derivatives. Cubic centimeters per minute, where T is time in minutes since the device began working. Oil continues to leak at a rate of 2,000 cubic centimeters per minute, just like it was before. Find the time when the oil slick reaches its maximum volume. Justify your answer. So do we know? Let's see. So the entering rate is still, I might call it E. It's still 2,000 cubic centimeters per minute. And we're looking for max volume, and we got to justify it. So if possible, we could try and use, extreme value theorem. Now, the overall rate, I like to call it A. So AT equals the initial amount plus what's been added, 0 to some time t, of the entering rate, minus what's being taken away. Oh, that should be the 2,000. Minus what's being taken away, that's removal rate. So this is your rate model. And then if you want to find absolute maxes and mins, you want to find critical points. So whatever that is, that's going to go away. I don't think they even give us an actual amount at any point or any kind of endpoints. So we might have to not use extreme value theorem, but it's going to be, you take the derivative of an integral, you get what's inside, and then you plug the limit in to the variable and times the derivative. So that's just going to be 2,000 minus 400 root t, which also makes sense. The overall rate is the incoming rate minus outgoing rate, right? And we're going to set it equal to 0 undefined. Define critical points. So this is all work you need to show. So 2,000 equals 400 square root of t divided by 400. So t equals 25. This is our critical point. There's only one, and there's no endpoint, so hopefully maybe a line check could help us. So we do a line check for a prime, 25, test a point. I think I'm going to test 0 over here. A prime is positive, then negative, so it's increasing, it's decreasing. So this is a critical point. This is a relative max, but it's going to be an absolute max, right? Even without endpoints, because we know that the graph just goes down forever on both sides. Now, justifying that's a little hard. So we say, and we're just looking for the time. So we say the oil slick reaches a relative maximum at time t equals 25 minutes by the first derivative test for relative extrema. How do you know that? Since a prime is positive on times less than 25 and a prime is negative on times greater than 25. So that just justifies relative max. And since this is the only relative extrema, it will be the absolute maximum, something like that. Now, I mean, I think the justification of it might be more like, well, because the derivative goes, it's decreasing, to the left and decreasing to the right forever. So it's got to be absolute max. So something like that. It's kind of a pain to justify, but we couldn't do extreme value theorem. C says, by the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Right, but do not evaluate. Right, but do not evaluate an expression involving an integral that gives the volume of oil at time found in part B. So I think this is where we're going to use our rate model. And it says by the time the device showed up, there was 60,000 already. So that's like your initial condition, right? Let's see. Hold on a second. Okay. Did they give us any other amount, any other time? By the time the recovery device, 60,000 pieces of oil had already leaked, right? But involving an integral that gives the volume of oil at the time found in part B. So 25 is what we're looking for. So the amount in general is going to be 60,000 plus what enters from that time forward. Okay. And the 25 was after the device arrived. And this is when the device arrived. So we're going to say time 0 is when the device arrived. And so we're going to do t 2000 dt minus 0 to t of 400 square root of t dt. So this is your rate model. And we're just going to use it to find the amount at 25. So it's going to be 0 to 25 of 2000 dt minus 0 to 25 of 400 square root of t dt. And then you don't need to actually find the answer. But you do need the dt's and everything. It needs to be set up really nicely. Okay. Last one, the cone. So this container has the shape of an open right circular cone as shown in the figure above. The height of the container is 10 centimeters. The diameter, which we probably want the radius from, is 5. Diameter is 10, radius is 5. Water is evaporating, so it's going out the top, evaporating. So its depth, h, is changing at a constant rate, negative 3/10 centimeters per hour. So again, they're giving us the negative. Usually they wouldn't even say that. You just have to assume, well, it's evaporating, so it's going down. Volume of cones, 1/3 pi r squared h. So probably going to have to use our similar triangles. You got an R, you got an H. Find the volume of the water in the container when H equals 5. So I think we should probably go ahead and try and get our volume formula in terms of just all H, because we're getting dH dt. We're talking about H here. So using similar triangles, R over H equals 5 over 10. So R equals 1/2 H. I'm going to plug that in to R. 1/2 H squared H. So the volume is pi over 12H cubed. That's what we're going to use. And then we can use that to go ahead and find the volume when H equals 5. So that's going to be 125 pi over 12. The units are something cubed, right? Centimeters cubed. B, find the rate of change of the volume of the water in the container with respect to time when H equals 5. Indicate units measured. So we're trying to find dV dt. So let's take the derivative of this. It's going to be pi over 4h squared dh dt. And it says that we're doing it, they gave us dh dt, right? dh dt equals -3/10 centimeters per hour. So h is 5, dh dt is constant, -3/10. So we get rid of one of these 5s. So dv dt equals -15 pi over 8 cubic centimeters per hour. And it's negative, as we expected, because we're losing water, losing volume. Show that the rate change of the volume of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. What is the constant of proportionality? Directly proportional. So the rate of change of the volume of the water, dv dt, is directly proportional to the exposed surface area. So we want to prove that. This is a constant in proportionality. Now, the surface area is going to be a circle, so it's going to be k pi r squared. So we're trying to get something times some number times pi r squared, which probably means we want our volume, we want everything to have r's instead of h's. So I'm going to go back to my volume, and instead of making it all h like it did originally, I'm going to say h equals 2r, plug that in, and get all r's. I think that's going to be helpful. So that's my volume in all r's. Now I'm going to take the derivative. Implicitly with respect to time, it's going to be 2 pi r squared dr dt. And, well, we don't have dr dt, but we do know that r equals 1/2 h, right? And so if we take the derivative of this, dr dt equals 1/2 dh dt. And dh dt, we do know, is always -3/10. So dr dt is -3/20. So we're going to use that in here. It's always constant. So if we plug that in, not plugging anything in for r, we get -3/10 pi r squared, which right there, that's dv dt equals -3/10 times the surface area. So we proved it. The constant proportionality is that. So we just got to say that. The constant of proportionality is -3/10. So it's kind of an interesting twist at the end. That's it. Bunch of good practice, related rates.